I am here to deliver a lecture on transformers. First, we will discuss about single-phase transformer. A transformer is a static device which helps to transform electric power from one circuit to another circuit with the same frequency. The voltage can be raised or lowered in a circuit, but with a proportional increase or decrease in the current ratings. The transformers are used in almost all electrical systems, from low voltage up to highest voltage levels. It operates only with alternating current, because if a direct current is given, then there won't be any electromagnetic induction. Depending on the electrical network where the transformer is installed, there are two types of transformers. One is single-phase transformer, another one is three-phase transformer. The operation of a transformer is basically on mutual induction. One of the main reasons that we use alternating AC voltages and currents in our homes and workplace is that AC supplies can be easily generated at a convenient voltage. It can be transformed very easily to a much higher voltages and then distributed around the country using a national grid. The AC current generates the alternating electromagnetic field. The magnetic field lines are moving through the iron core of the transformer and it is linking with the transformer secondary. Thereby, it produces EMF in the secondary windings also with the same frequency of the primary voltage. Let us discuss about the construction of the transformer. So this is a transformer. Transformer, it mainly consists of the core, windings and the isolation. So here the construction, the windings are placed over the iron core and we will feed input supply across the primary winding and secondary winding. Across the secondary winding we can connect the load. The main parts of the transformer are windings, core and isolation. The windings should have small resistance value and usually they are made of copper or rarely aluminum are used. They are wound around the core and must be isolated from it. Also, the winding turns have to be isolated from each other. The winding should be isolated from the core as well as the winding turns, the primary and the secondary sides has to be isolated from each other. The transformer core is made from very thin steel laminations which have high permeability. The lamination have to be of very thin. The values will be usually 0.25 mm to 0.5 mm because of decreasing power losses. So if the laminations are thin, then we can reduce the eddy current losses in a transformer. So there are mainly two types of losses in the transformer. One is the core loss, another one is the eddy current loss. So by using thin laminations in the transformer core, we can reduce the eddy current losses. They have to be isolated from each other. That is, the laminations have to be isolated from each other. And usually, the insulating varnish is used for that purpose. The transformer insulation can be provided as dry type or liquid filled type. The dry type insulation is provided by synthetic resin, air, gas or vacuum. It is used only for small size transformers below 500 kVA. The liquid insulation type usually means using mineral oils. The oil has a long life. If you use liquid type of insulation, then it will be having long life, good isolation characteristics, overload capability and also provides transformer cooling. Mostly big transformers and all, they are using oil insulation. Now we will discuss about the working principle of transformer. So as we know, so already we discussed, it mainly consists of iron core, windings. The windings are wound over the legs. The main principle of operation of transformer is mutual induction between the two circuits, which is linked by a common magnetic flux. A basic transformer consists of two coils. One is the primary winding, another one is the secondary winding. The two windings are electrically isolated, but it is magnetically coupled. If the second coil circuit is closed, a current flows in it and thus electrical energy is transferred from primary to the secondary via the magnetic circuit. The alternating current supply is given to the first coil and hence it can be called as primary winding. If AC supply is given to the primary winding, it develops the alternating flux. Then that flux will be linking with the secondary winding which is placed very close to the primary winding So due to the change in flux in the secondary winding, EMF will be induced in the secondary winding also. The EMF which is induced in the primary coil is called self-induced EMF. The EMF which is induced in the secondary winding is called mutually induced EMF. The self-inductance and the mutual inductances are represented by the term L and M respectively. The energy is drawn out from a secondary coil and thus it can be called a secondary winding. In a short, a transformer carries the following operations. It transfers electrical power from one circuit to the another. A transfer of electric power without any change in frequency. Transfer with the principle of electromagnetic induction. The two electrical circuits are linked by mutual induction. Mutual induction is the main property, principle behind the transformer. The electrical transformer has primary and secondary windings. The core laminations are joined in the form of strips. In between the strips, you can see that there are some narrow gaps. Both the coils have high mutual inductance. The mutual electromotive force is induced in the transformer from the alternating flux that is set up in the laminated core due to the coil that is connected to the source of alternating voltage. That is, the primary winding will be always connected to the alternating voltage. So, alternating flux will be set up. That flux will be linking with the secondary. So, EMF is induced by mutual induction property. Most of the alternating flux developed by this coil is linked with the other coil and thus produces the mutually induced electromotive force. The so produced electromotive force can be explained with the help of Faraday's law of electromagnetic induction. That is, Faraday's law of electromagnetic induction is EMF will be developed whenever there is a rate of change of flux in it. That is, E is proportional to d phi by dt. Here, this alternating flux will be produced by change in alternating current. This alternating current is due to the alternating supply which is connected across the primary winding. So, by Faraday's law, we can say the EMF induced E is equal to M into di by dt. M is the mutual inductance. The types of transformers. The types of transformers differ in the manner in which the primary and secondary coils are provided around the laminated core. According to the design, transformers can be classified into two types. First one is the core-type transformer and second one is shell-type transformer. The difference between the two types of transformers are the core-type and shell-type transformer difference is that core-type transformer, the winding surrounds the core, whereas in shell-type transformer, the core surrounds the winding. First, we will discuss about the core-type transformer. The magnetic core of the transformer is made up of laminations to form a rectangular frame. The laminations are cut in the form of L-shaped strips as shown in the below figure. For avoiding the high reluctance at the joints where the laminations are butted against each other, the alternate layer is stacked differently to eliminate continuous joints. This is a diagram for a core-type transformer. Half of each winding, actually in practical case, half of each winding is placed side by side or concentrically on the leg of the core as shown in the below figure. For simplicity, the primary and the secondary winding is located on the separate leg of the core. The insulation layer is provided between the core and the lower winding and between the primary and secondary winding. For reducing the insulation, the low winding is always placed near to the core. The winding is cylindrical and the lamination is inserted later on it. The second type of transformer is shell-type transformer. The laminations are in shell-type transformer. The laminations are cut in the form of E shapes or I shapes. To reduce the high reluctance at the joints where the laminations are butted against each other, the alternate layers are differently stacked to eliminate the continuous joints. This is the diagram for shell-type transformer. The shell-type transformer usually transformers have three legs. The center leg will be of wide when compared to the outer legs. It carries the center leg mostly carries the most of the flux and the side limb carries the half of the flux. Hence the width of the center limb is about double that of the outer limbs. This is the primary winding and secondary winding is also shown here. This flux will be developed by alternating current and this magnetic lines will move through the iron core of the transformer. The primary and the secondary, both the windings are placed on the central limbs in shell-type transformer. The low voltage winding is placed near the core and the high voltage winding is placed outside the low voltage winding to reduce the cost of insulation placed between the core and low voltage winding. If low voltage winding is placed near the core of the transformer, the insulation will be cost will be reduced when compared to high voltage winding placed near the core of the transformer. The windings are cylindrical and the core laminations are inserted on it. Coming to the application of single phase transformers, the transformers are used everywhere wherever the voltage need to be stepped up or stepped down, and in most of the applications everywhere from generating station, distribution and transmission, everywhere these transformers are used. The advantages of three single phase units are transportation, maintenance and a spare unit available. The single phase transformers are widely used in commercial low voltage application as electronic devices. Therefore, if you want to use transformers in electronic devices, mainly it is used for stepped down application. So in the output of the secondary side, usually rectifier circuit is connected to convert this AC voltage to DC voltage. The next part is the regulation of the transformer. It is an important characteristics of the transformer. So the voltage regulation of a transformer can be defined as it is the percentage difference in voltages between when the transformer is fully loaded and no load to the full load voltage. Here the voltage regulation is E2 in percentage, it is E2 minus V2 by V2 into 100, where V2 is the voltage across the load terminals when transformer is under loaded condition, and E2 is the voltage across the secondary terminal when it is under no load condition. Usually this loaded voltage will be less than the no load voltage because of the I2 is the voltage drop in the transformer. Efficiency of a transformer. So here the efficiency of a transformer, the transformer is the most efficient electrical apparatus. So generally the efficiency can be defined as output by input. The transformers, as I said, these transformers are highly efficient electrical device. The transformer efficiency will be lying between 95% to 98.5%. As transformer being highly efficient, output and input are having nearly the same value, and hence it is impractical to measure the efficiency of a transformer by using the usual method of output by input. Instead of that, we can use the alternate method. The better method to find efficiency of a transformer is efficiency equal to output by input. Here, the output is replaced by input minus losses. So input by input is equal to 1. So it becomes 1 minus losses by input. We know very well, in transformer there are two types of losses, core loss and iron loss. So the losses are the core loss, otherwise iron loss is represented by W suffix I, and the copper loss is represented by I1 squared R1. So 1 minus losses, that is copper loss plus iron loss, divided by input. Input is V1 I1 cos phi 1. V1 is the input voltage, I1 is input side current cos phi 1. So phi 1 is the angle between input voltage and input current. Then efficiency, again it can be written as 1 minus, that is dividing the numerator and the denominator, that is I1 is a common factor, the numerator denominator the second term. So reducing that, you will get 1 minus I1 R1 by V1 cos phi 1 minus, separating the terms, VI by V1 I1 cos phi 1. To find the maximum efficiency, we can differentiate this above equation, efficiency equation with respect to I1 and equate to 0. We will get the maximum condition for maximum efficiency, that is D efficiency, that is a derivative of efficiency with respect to I1 equal to 0. That means, so the derivative of differentiation of constant term is 0 minus R1 by V1 cos phi 1 plus VI by V1 I1 squared cos phi 1. So equating that term equal to 0, then we will get the condition for maximum efficiency will be R1 by V1 cos phi 1, that is equal to VI by WI by V1 I1 squared cos phi 1. So rearranging the terms, I1 squared R1 equal to R1 by V1 I1 squared cos phi 1, that is equal to WI by V1 I1 squared cos phi 1. Then removing the denominator, both the denominators are equal. So removing that, we will be getting I1 squared R1 equal to Wi. That is, this is a condition for maximum efficiency of a transformer. That is, efficiency of a transformer will be maximum when copper loss and iron losses are equal. That is, copper loss equal to iron loss. At this condition, the efficiency of the transformer will be maximum. All-day efficiency of a transformer. It is an energy-based efficiency. The all-day efficiency is called energy-based. Apart from the efficiency of the transformer, we can calculate the all-day efficiency also. It is the energy-based efficiency calculated for distribution transformers. In distribution transformers, the loading will be varying continuously for 24 hours a day. As core loss is independent of load, the all-day efficiency depends on the copper losses. We define it, the all-day efficiency can be defined as the ratio of output energy delivered to input energy for a 24-hour cycle. High energy efficiencies are achieved by restricting core flux density to lower values, as the core losses are independent of flux density, by using relatively larger cross section or larger iron or copper weight ratio. The next topic is the auto transformer. Auto transformer, it is also a kind of electrical transformer where primary and secondary shares common single winding. So basically it is a one winding transformer. The theory of auto transformer is, in auto transformer, one single winding is used as primary winding as well as secondary winding. But in two winding transformer, we can compare this auto transformer with the two winding transformer. In two winding transformer, we will be having two separate winding which are called primary winding and secondary winding. But in auto transformer, only one winding will be there. So that winding will act as primary, the portion of that winding will act as a secondary. The diagram is shown in the next slide. The diagram is, this is the diagram of auto transformer. Here, this A and B, AB acts as primary. This is the input supply. This one winding is used here. So this V1 is input supply, I1 is input current. This AB acts as primary. The number of turns in the primary can be taken as N1, and some of the current. Here the tapping is provided at point C. So this part B and C will act as a secondary. Then current through the secondary path will be a difference of these two currents, I1 and I2. So V2 is the secondary voltage. So the total number of turns in the secondary can be taken as N2. If V1 is voltage applied across the winding, that is between A and C, that acts as primary, the voltage per turn will be V1 by N1. Hence the voltage across the portion V1 by N1 will be the voltage across the primary. Then next one is the voltage across the portion VC will be, by voltage division principle, we can say the total voltage is V1, the applied voltage is V1 into the particular turns N2 divided by total turns N1. So the V2 is equal to V1 by N1 into V2. When load is connected between secondary terminals between B and C, the load current I2 starts flowing. The current in the secondary winding or common winding is the difference of I1 and I2. So here we know very well, this auto transformer has only, it shares one winding as primary as well as secondary. So definitely there will be saving of copper. Let us discuss how the copper can be saved in the auto transformer when compared with the two winding transformer. That is saving of copper in auto transformer compared to conventional two winding transformer. We know that the weight of copper of any winding, the windings are made up of copper. The weight of the copper depends on the length of the winding as well as cross-section area. The length of the winding depends on number of turns in the winding, and the cross-sectional area depends on the current rating of the winding. So the length proportional to the number of turns and the cross-sectional area of the winding proportional to the current carrying capacity. So weight of the copper in winding is directly proportional to the product of number of turns and rated current of the winding. Therefore, weight of copper in section AC, that is primary, is N1 minus N2 into I1. And similarly, the weight of copper in the section BC is N2 into current through that, I2 minus I1. So the total weight we can add both N1 minus N2 into I1 plus N2 into I2 minus I1. Then simplifying that equation, assuming N1 I1 equal to N2 I2, so we will get 2 N1 I1 minus 2 times N1 I1 minus N2 I1. The previous slide was, the previous one was about, this is a 2 times N1 I1 minus N2 I1 as the weight of the auto transformer. Here this is the weight of the two-winding transformer. Let us compare the weight of the two-winding transformer with the weight of the auto transformer. So we know very well, in two-winding transformer, the primary winding is considered as a primary winding will be having N1 number of turns and it carries the current I1. Similarly, N2 is the number of turns in the secondary winding and I2 is the current in the secondary winding. So here N1, the total weight, we know very well, the length of the winding depends on number of turns in the winding and the cross-sectional area depends on current carrying capacity. So the weight of the copper is proportional to the current number of turns and current. So it becomes a two-winding transformer. Since it has two separate windings, the weight of the copper is proportional to N1 I1 plus N2 I2. Assuming N1 I1 equal to N2 I2, so it becomes 2 N1 I1. Let us assume W suffix A and W suffix TW are the weight of the copper in auto transformer and a two-winding transformer respectively. Hence, dividing the both, that is previous equation. This equation is, this one is the weight of the auto transformer and this one is the weight of the two-winding transformer. Here we are dividing both. W suffix A is the weight of the auto transformer. W suffix TW is the weight of the two-winding transformer. 2 N1 I1, 2 times N1 I1 minus N2 I1 divided by 2 N1 I1. Then simplifying this, 2 to cancel, N1 I1 minus N2 I1 by N1 I1. Then these two are equals to 1 minus N2 I1 by N1 I1. Then we know very well, this I1 is common, it can be cancelled. N2 by N1 is the transformation ratio of the transformer. It is usually represented by K. So N2 by N1 is replaced by K. It becomes 1 minus K. So WA. So here WA is here. WA equal to WTW. That is the weight of the two-winding transformer into 1 minus K. Usually this K varies from 0 to 1. So if you substitute any value between 0 to 1, so obviously the weight of the auto transformer will be, for example, this is a 0.6. 1 minus 0.6, 0.4. 0.4 times two-winding transformer weight will be equal to the weight of the auto transformer. By this method, by this derivation, we can understand this weight of the auto transformer will be less than the weight of the two-winding transformer. Saving of that, so definitely there will be a saving of copper in auto transformer when compared to two-winding transformer. So it can be shown as that is weight of the two-winding transformer minus weight of the auto transformer equal to K times two-winding transformer. K is nothing but a transformation ratio, turns ratio of the transformer. The next one is the three-phase transformer. The first slide itself we have seen there are two types of transformer based on the application where it is installed, based on electrical network where it is installed, and also based on the input electrical supply. There are two types of transformers, single-phase transformers and three-phase transformers. The three-phase transformers are made of three sets of primary and secondary windings. Each set wound around one leg of an iron core assembly. Essentially, it looks like three single-phase transformers sharing a joined core as shown in figure. Here, this is three separate primary and secondary windings are there. So this primary and secondary windings in three-phase transformers, there are three methods of obtaining three-phase transformers. It can have three independent connections, and second one is it can be connected in star format, and third one is it can be connected in delta format. All the primary windings can be connected in star format or delta format, or secondary windings can be connected in star format or delta format. There is those sets of primary and secondary windings will be connected in either star delta or star configuration to form a complete unit. The various combinations of ways that these windings can be connected together. Whether the winding sets share a common core assembly or each winding pair is a separate transformer, the winding connection options are the same. Here the primary and secondary connections may be star-star connection, star-delta connection, delta-star connection or delta-delta connection. Usually in star-star connection, the phase voltage will be a line voltage VL by root 3. Then phase voltage and line voltage will be different. But in a star connection, the phase current and line current will be same. In delta connection, phase voltages and line voltages are always equal. But this phase current will be line current divided by root 3. So based on the voltage rating and current rating and the application where it is used, we can select any type of connection, star-star connection, star-delta connection, delta-star or delta-delta connection. The reasons for choosing a star or delta configuration for transformer winding connections are the same as for any other three-phase application. Star connection provides the opportunity for multiple voltages, while delta connections enjoy high level of reliability. If one winding fails open in delta connection, the other two can still maintain full line voltages to the load. As I said earlier, in delta connection, VL equal to V phase. So wherever higher reliability is required, then when one winding goes out, then we can have with the other two winding, we can have the voltage. We can get the voltage, required voltage. So this is this is the star connection. Here this is a phase, first phase, second phase, third phase, three phase windings are connected. In a three phase winding, the three windings are displaced by 120 electrical degrees. So this is second one is called delta connection. In delta connection, it forms a closed mesh. So here also all the three windings are displaced by 120 electrical degrees. So the first, this one is taken as a reference phase, so 0 degree, and second one it is this from the first with respect to the first phase. The second phase is displaced by 120 electrical degrees. Then with respect to the first phase, the third phase is displaced by 240 electrical degrees. The phase displacement between, that is 360 divided by number of phases, 360 divided by 3 equal to 120 electrical degrees. So this way the three-phase transformers can be connected. The three-phase transformers can be connected in star format or delta format based on the application. Thank you.